This is Chapter 8, Deformation and Metamorphism, Lecture 1. Our goals for this chapter include to investigate the processes of deformation and metamorphism and look at the resulting rocks and structures. We will also look at the plate tectonic settings of deformation and metamorphism, and we will observe how structures and metamorphic rocks are seen in different landscapes. We'll start with this one. So this is the Valley and Ridge Province. It's southeastern Pennsylvania. We see curving mountains and ridges, sort of alternating with lower areas. This river flows southward, and it cuts across the ridges and lower areas. And we can take a cross section of this too. We have folded Paleozoic sedimentary rocks. Those rocks were deposited in shallow seas, along shorelines, and in rivers or along rivers. They were folded, faulted, and heated several times during the Paleozoic, and then they experienced major deformation 300 million years ago when Africa collided with North America. So a lot happened to these rocks. Let's think about the basic concepts of force and stress. Force is push or pull. We express that as the amount of acceleration experienced by a mass. So you have an arrow denoting force and the mass itself. What happens if the same amount of force is applied to two different wooden pillars? Well, this wooden pillar is larger. This one is much smaller. The stress that results, it's greater if the same amount of weight or force is distributed on a thinner pillar, because stress equals force per area. There's a few different kinds of stress. We'll start with confining pressure. So that's where you have the same amount of stress on this mass from each direction or from all directions. Differential stress is where you have different amounts of stresses, like denoted by larger arrows versus smaller arrows, coming from different directions. So that'll impact the mass differently. We'll look at the strength of a rock. First off, on the rock or the mass, we have small stress being applied. It might cause this rock to contract but remain undeformed. If we have an increase in stress, that might leave the rock undeformed if the strength of the rock is greater than differential stress. If we apply more stress, we'll call that too much stress. It'll make a rock fail structurally by flowing or fracturing. And sometimes it's easy to get lost in these diagrams, but we'll break it down. So what we have here is a diagram showing what happens under increasing strength with greater stress and increasing depth within the earth. Okay, so in shallow levels right here, within the Earth's subsurface, the crust deforms by fracturing or other brittle deformation, fracturing, faulting. There's an area underneath the Earth's surface that we call the brittle ductile transition. At that depth, the rocks might begin to flow ductily and fold and flow. So at these great depths, the rocks flow more easily and the strength of the crust decreases. And we have really an increase in temperature and pressure at this depth. All right, so more on how rocks respond to force and stress. Again, right here, a small amount of stress, this block remains unchanged, as if I were holding some limestone in my hand and I try to squeeze it with my hand and nothing happens. It might compress a little bit if I were really strong, but I'm not. So we can also have displacement, where this rock has moved from one place to another. And we have an example here of displacement along this line. That's a fault. You could have rotation of the rock. It can tilt or spin horizontally. Like these rocks are tilted from their original horizontality. Or we can have strain. That's where a rock can deform internally under stress and change its size or shape. And we have these squished pebbles as an example of strain. All right, so there's 3 kinds of stress we want to talk about and some resulting structures. Starting off, compression. So at shallow levels within the earth, a rock will deform brittly by fracturing or faulting. And then at deeper levels, where rocks are hot enough to flow with greater pressure as well, ductile folds can form under compression. Then there's tension. Tension can form fractures at shallow levels within the earth as it's sort of pulled apart. Tension is kind of harder to achieve the deeper you go within the earth. But if a rock is under differential stress, it can be stretched under tension that way. And it's harder to achieve at depth because there's so much confining pressure on a rock. And then shear. So we have stress in this direction and in that direction. It causes the rock to shear. And that forms faults at shallow levels within the earth. In deeper levels, shearing will be distributed across a wide zone called a shear zone. So just to show you again, at shallow levels within the earth, the rocks will fracture, and this is compression. And this is tension, and this is shear. And then deeper, we'll see under the same types of stress, we'll see the rocks flowing, and this is what they will look like in an idealized version. Okay. So there's going to be a change in deformation as temperature and pressure increase with depth. At shallow depths, rocks will fracture and exhibit brittle behavior as seen in this. They'll break. Deeper within the earth, we see the rocks flowing. They exhibit ductile behavior. They fold like this. There will also be a change in how the minerals respond as temperature and pressure increase with depth within the earth. So at shallow depth and low temperatures, perhaps the minerals are unaffected. I see some fracturing here. I don't see a whole lot else. Deeper, with higher temperatures, minerals can recrystallize or new minerals can grow into larger, smaller crystals as well. Let's talk about some different types of fractures. This is a joint, and that's a crack rather, where a rock is pulled apart. Okay, and this is a nice example of jointing in an outcrop. This is a fault. That's where rocks have slipped past one another. There's displacement like that. And here's a really nice outcrop example. We see these 2 parts used to be together, but now they've slipped past one another. Let's think about the stresses that form joints. So we have burial and tectonic forces being the stresses that mostly form joints. In some cases, joints form as rocks get warmer or cooler, as in the case of columnar joints forming from cooling in an igneous rock. And when deeply buried rocks are uplifted to the surface, the pressure is reduced, and that can form unloading joints. Like so. These are unloading joints. All right. So here's how a rock deforms with compressive stress. It's applied parallel to the axis of the cylinder, like so. And there's plenty of laboratories that test this to determine the strength of something like cement that's used in construction. So, in this case, compressive stress is applied. As stress increases, the internal strain increases, and that's going to cause bulging as the cylinder kind of shortens. So there's no change here, but it's starting to bulge. I've actually done these tests myself in the lab, and you can apply that stress. You get to the bulge part, you know, anticipation kind of builds, but then the applied stress exceeds the strength of the rock and the cylinder fractures. Makes a loud sound in the lab because it fails. If you continue to apply stress, you'll have slip along the fracture, and in the lab you don't want to do that. You want to stop the stress there because you already have the data to determine at what point the rock fails. All right. So we'll talk about faults. So there's something with faults that we call strike. If you were to take one side of a fault or one half of it, or look at the plane of a fault and flood it with water, we can determine the direction of strike, where it hits or intercepts the fault plane right here. It's the horizontal line on an inclined surface. If you were to flood an area with water, it will intersect or strike the fault surface in a certain direction. That's strike. Let's talk about dip. These two things go hand in hand in geology. Dip is the inclination of a fault surface, where, say, water will pour down the dip of a fault. These are both angles. We don't need water to determine strike or dip. It just helps us illustrate the concepts. So we're striking in this direction, and the surface dips in this direction. All right, so this is a strike-slip fault. That occurs like where slip occurs along a fault in a horizontal direction, parallel to strike, just like so. This is a dip-slip fault, and slip along that fault is parallel to how the fault plane dips, so down in this direction. You can also have oblique slip. This is an oblique slip fault. Slip along that fault is in a direction that is oblique to the strike plane. And now we can think about different parts of a fault. Okay, so here's one half, another half of rock that are intersected by a fault plane. The hanging wall, and we're using this guy to illustrate the point, it's the block above the fault. Say if you were a miner in the subsurface, you could hang your lantern up there so you could see what you were doing. The footwall is the block below this guy's feet where he could walk. This is just to illustrate. So to show you in an outcrop, this is the hanging wall and this is the footwall. There's a few different types of faults that we'll think about. The main types of faults include a normal fault, where the hanging wall moves down relative to the footwall. There you go. Normal fault. Or you could have a reverse or a thrust fault, where the hanging wall moves upward relative to the footwall. You can also have a strike-slip fault as such. That's where two sides move horizontally relative to one another. And we say this is left lateral because it's moving leftward relative to this side. That's a left lateral fault. If you're on one side of a strike-slip fault and a feature is offset to the left across the fault, that's how you know. You say it's left. Right lateral would be the opposite of that. If you're on one side of a strike-slip fault and a feature is offset to the right across that fault. Okay. So those are faults. Now let's think about folds. So compressive stress causes shortening. We see the stress applied with these arrows, often accommodated by folding. All right, so we see that in like a block diagram. This is an anticline. That's where your rock layers are generally warped upwards, and the oldest rocks in the anticline are in the center of the fold. Syncline is kind of the opposite here. The rock layers are generally folded down, and the youngest rocks are located in the center of the fold. See an anticline here in the outcrop view, and a syncline as well. So we can also think about domes and basins. Domes are layers that are uplifted in a circular or elliptical area and dip away in all directions. And then the oldest rocks are in the center of the dome. The basin, that would form by folding, and the layers are going to dip toward the center of the basin from all directions. The younger layers are in the center of the basin. This is a monocline. So in monoclines, we have nearly flat layers that bend down or dip in one direction, and then they flatten out again. Here's an outcrop view of that. We can think about as well the geometry of folds. There's a way of describing these. This is all just a vocabulary that's used to standardize communication in geology so that most everyone knows what everyone's talking about when they describe something in a landscape. All right, so we have a hinge. That's where the fold is most sharply curved. And then we have a limb on one side and a limb on the other side of the fold. Those are planar or less curved parts of the fold. This is a plunging fold, and that occurs if the hinge is inclined from horizontal. It's kind of inclined that way. This is an upright fold. This plane that we draw through is the axial or axial surface of the fold. This is the fold axis. I can draw it out this way. The fold is upright if the axial surface is perfectly vertical. We'll say this is an asymmetric fold because the axial surface is inclined. And this is an overturned fold. And we say something is overturned if one of its limbs has been rotated more than 90 degrees. Now we learned about mineral cleavage. This is rock cleavage. We have stress applied to a rock that causes it to shorten and develop features. So here we have a cleavage plane. It's not mineral cleavage, it's rock cleavage. So it develops these features perpendicular to the direction of shortening, and we call that rock cleavage. This is what it might look like in an outcrop. This as well. So we see these sort of linear features, and that's due to stress that's applied. We can also have foliation. And foliation is any planar metamorphic fabric, including cleavage. It's usually used for more strongly metamorphic rocks. So we can start off. This is schistosity. That happens with mica typically, and it's foliation that results from stress applied to a rock, and it's in a dominant orientation, and it reflects a lot of light. It's shiny, sparkly. That's schistosity because all of these minerals are aligned in one direction. You can also have gneissic foliation. That's where you get alternating lighter and darker bands in metamorphic rocks. These are the bands. All right, we see that in a lot of metamorphic rocks. You could also have flattened pebbles. That's where the foliation is parallel to the flattened shapes of the pebbles. Or you could get foliation from shearing. So basically, ductile shearing flattens and smears out the mineral grains. And we will stop here for today.